Hey guys, I started recording. I'll get ready to present in about like 2 minutes here. 3:32. Can you guys hear me?
Yep, you're loud and clear.
All right, sweet.
Big group, you nervous?
Uh, there's like 2 pages of people, so we'll see.
Hey, Paul, if you're trying to talk, you're still muted.
Can I hear you?
My bad, guys. Okay. So, yeah, my project was on exploring interpretability in machine learning and how interpretation of neural networks can be fragile. So yeah, can neural networks be fragile? So can interpretations of neural networks be fragile? If we look at the image to the left or to the right here, in the test example XT here, that can be a certain image of some kind that a model classification model is trying to predict. And we can see XT plus delta, which is right here, which is the new modified attack image. The contours and the decision boundaries corresponding to a loss function is shown here. And we can see that the direction of the gradient of the loss with respect to the input space. So this would be the gradient loss for the original image, and this would be the gradient loss for the attacked image. Um, yeah, neural networks with many parameters have decision boundaries that are roughly piecewise linear with multiple transitions. And a small attack changes the direction of the gradient loss from vertical to horizontal in this case, impacting the feature importance analysis while keeping it within the decision boundary. So it's able to keep the same prediction while differing the interpretation of the image. So yeah, neural networks from this is like all hypothetical. We're looking, so are they fragile? And this is pretty much what my project is aimed at. We want to see if certain attacks on images affect the interpretation while keeping the prediction, and what kind of attacks affect the interpretation the most while keeping the same prediction. Yeah, so why is this important? We want to generate attacks on images to reduce indistinguishable inputs for classification models that still have the same predicted values. We want to expose fragile neural networks to better understand different classification models to better them in the future. So my implementation, I used a SqueezeNet classification model. It uses a 1x1 filter that normally is used with a 3x3 filter to reduce computation time. It uses the 1x1 filter as a bottleneck layer to reduce step, and downsamples late to keep a big feature map. And we want to attack these using an iterative attack. So it takes a series of steps in the direction that maximizes a differential exam dissimilarity function between the original and attacked image. And the different types of attacks I will be using in my implementation will be random, top K, and mass center. Random, just each pixel is randomly perturbed by plus or minus E, and the top K seeks to attack the feature importance map by decreasing the relative importance of the K initial most important features. K in this case will be 1,000. And the mass center is designed to result in maximum spatial displacement of the center of mass. And to see which attack is most effective, we'll be using various classifications like prediction confidence, percent of most salient 1,000 pixels in the original image being in the new 1,000 most important pixel, the rank correlation between the saliency maps, and the L2 distance between saliency maps. And L2 is practically the mass center. So it's changing the distance between the mass centers. And here we can see a little example of what the saliency map and how the SqueezeNet classification model interprets an image of these two llamas here. You can see two llama heads from the saliency maps there. So my evaluation after the mass center, you can see that it attacked the center of mass here. This is the original. So for the following slides, it's going to show you a 4-grid image with the top row being the original and the bottom row being the attacked images. And we can see that the saliency map is pretty different. The top is the original and it's math center. So the confidence doesn't change, but only 2.3 of the 1,000 most salient pixels are in the original. And the rank correlation between the saliency maps is about 0.26. The distance between mass centers is about 65 pixels. In the random, the confidence changes an insignificant amount, but the most salient pixels are a little bit more relevant, and the rank correlation between is a little bit higher as well. And the distance between the mass center saliency is 1 pixel, which we can see. And then the top K. So this is a significant amount of change in the confidence. None of the 1,000 most salient pixels are in the original image or among the 1,000 most salient pixels of the attacked image. And the rank correlation is pretty low, and the distance of the mass center is also pretty low as well. So from that experiment, we see that the confidence of for mass center and random did not change much. So the prediction of them still lies pretty greatly, and the mass center and top K saliency maps differ the most from the original. So the mass center from this experiment, we see that the mass center is the best type of attack to keep its original prediction while changing the interpretation of the image. And yeah, I'm open to a few questions and a discussion.
Yeah, so Paul, I'm your discussant.
Yeah.
First quick question for you. Is this all code that you wrote, or were you working off an existing code base?
So yeah, there was a GitHub repository of an existing code base. They really didn't go ahead into discussing the similarities between the different types of attacks, but just like the certain they chose the mass center and decided to depict the mass center as the most important type of attack and went on their research from there. So I decided to use the different types of attacks like the random and the top K and just find the similarities between all those attacks. And that is what I implemented in my project.
Got it. And then one more. What kind of applications do these attacks have? And more specifically on that question, is it more looking at things like noise and corruption compression, or are we expecting malicious actors to be performing attacks like these on images against networks?
So the main purpose of these attacks were to just show that neural networks can be and could be susceptible to fragility So yeah, like we can now see that certain models that use neural networks are susceptible to different types of interpretability while keeping the same prediction. So from what I'm understanding of your question is that we use these attacks to just show that these neural networks can be fragile and be conscious of the fragility of neural networks.
Got
Um,
it.
is that all? I think
Yep, I
I
think so.
went a
And I think we're
little
out of
ahead of
time.
time. Yeah. All right. Thank you guys. Yeah, hi. Do you guys hear me?
Yeah, I can hear
Yep.
you. Yep, I can hear you.
Yeah, okay, I'll get started. So, hello, my name is Tongwon Lee. I'm going to present towards identifying robustness of out-of-distribution score on variational autoencoder. So, deep learning models have revolutionized neural fields, showcasing exceptional performance in tasks ranging from computer vision to natural language processing. However, their potential is hindered by a critical challenge: their susceptibility to out-of-distribution data and real-world scenarios. So out-of-distribution is the distribution that does not belong to the distribution that the model has been trained on. As we deploy deep learning models in safety-critical applications like autonomous vehicles, the stakes are high. The vulnerability of these models to unexpected OOD data raises concerns. In the realm of autonomous vehicles, for instance, the ability to accurately detect OOD scenarios is paramount. Consider a situation where the model encourages an object it hasn't seen during training. A failure to distinguish such unknowns could result in accidents or malfunctions. To address this, our motivation is clear. We need effective OOD detection methods tailored for the unique challenge. So this leads us to the likelihood regret score, a novel metric proposed. Likelihood regret, an out-of-distribution detection score for variational autoencoder. Here's a basic explanation of how likelihood regret is computed. At first, we train a generative model such as a VAE. We calculate the likelihood of OD samples using the trained model, and then calculate the likelihood after optimizing the model for the sample. The likelihood regret is the difference between the samples. So we want to assess the ability of LR dealing with different versions of image which simulates real-world scenarios. To evaluate the effectiveness of LR, we conducted experiments using diverse datasets. This includes transformed, corrupted, and adversarial examples. We generated adversarial dataset using fast gradient time method, which is a well-known type of an adversarial attack. We trained VAEs on standard datasets like MNIST and fashioned MNIST. Moving on. Moving on to our research, we observed the VAE's performance across various datasets. This is the histogram that depicts the distribution of score. The left picture is the histogram of LR computed by VAE trained on MNIST. When exposed to transport MNIST samples, our VAEs demonstrated a robust ability to detect these variations. However, noteworthy observation is the widespread of distribution of the fashion MNIST, possibly stemming from the VAE's challenge in reconstructing the fashion MNIST dataset. Conversely, in the right picture, which is the histogram of likelihood regret computed by VAE trained on fashion MNIST, the LF score effectively distinguished OOD samples. An intriguing observation is the similarity in the LR distribution computed for MNIST and EMNIST, suggesting that the VAE trained on fashion MNIST has learned diverse features, including rotation. So we also evaluate the likelihood regret score on using AUC-ROC metric, which is a well-known metric for out-of-distribution tests. We compare likelihood regret score and the likelihood, which is also used for OD tasks. The table shows the AUC-ROC computed by VAE trained on MNIST. The AUC-ROC for both scores are high. For
OD samples. However, their performance diminished with corrupted samples. This may result from the vulnerability of DAE trained on clear image facing corrupted image. So as we delve into the insights gained from our experiments, we recognize the importance of LR in enhancing the robustness of deep learning models. The implications of our work extend beyond experimental setups. It has the potential to impact real-world applications, especially those demanding high levels of reliability and safety. Yeah, thanks.
Hey, I just have a few questions for great presentation. So question one, with the LR scores, is there a clear solution or path for the future for out of distribution problems? I know you touched upon it a little bit ago, but for the models, or is the LR scores a way to identify the models with too high of the out of ordinary distribution problems?
Yeah, it was like this is the score proposed by researchers, and they present this paper on, I remember, Europe 2021. So usually the generative models relies on likelihood to generate some image. So they usually say like if the likelihood is high, the image is more realistic. But nowadays, when the other researchers checked it, the likelihood is not that really good score for OD detection, because like so for example, when a VA trained on MNIST or CFAR10, they got an image that they have not seen during the training. They also can have like a high likelihood. So that's like motivation one for why likelihood regret was proposed. And the researchers said like they think so VA has like two things, so like encoder and decoder. So usually when we trained on some like training data sets, the encoder and decoder has optimized for that data set. So like using other like SGD or other optimizer, they're trained on that data set. However, when they exposed to like other data sets, such as like they haven't seen during the training, that's like out of distribution, and if they optimize the decoder using the new sample, they might optimize further. So like so that's like the motivation for the LR score.
Okay, awesome. Could you go back to the slide with the results? Yeah, so could you explain again why when the model was trained on the FMNIS, why the MNIS and the EMNIS were like so similar in the distribution?
I missed like the part. So EMNIS is like just the rotative version of MNIS.
Oh, okay.
So yeah, so I thought like when we compared the EMNIS result from the LR score trained on VA trained on MNIS and fashion MNIS, we can see that in the left picture, the EMNIS has like not the very same score with the MNIS, but on the right picture, we can see like the EMNIS and the MNIS has like a similar distribution. So it's the conjunction. It's not, I'm not sure, but I think because like in fashion MNIS, they have like lots of lines, and the model can learn the rotation thing, I guess, like features. So I thought that's why they have like similar distribution on the sample on the score.
Okay, awesome. Thank you. I think that's it for me.
Okay, thanks.
Can you guys hear me?
Yes, I can hear you.
Yep. Hello, my name is Hyungjuna. I will introduce about the hot car fatalities using YOLO. Yep. Heart stroke can be a trade year-round in some areas, so parents and others need to be alert to ongoing risk that children can die in a hot car. So it's never safe to leave a child unattended in vehicles, even with the windows cracked or the vehicles parked in the shade. The interior temperature within the car can reach dangerous level in short period of time. So to avoid such tragedies, I aim to detection technologies that could remind parents or guardian that children have been left in the car. So the implementation sequence downloads the YOLO version 5 model, and the dataset is to be trained, and the lab dataset is separating the training dataset and validation dataset, and the test dataset and labeling is performed. And we can train the model using the YOLO version 5 model, and the label dataset is performed the appropriate hyperparameter tuning. As a result, it can detect the children, adults, and other objects such as child seat in the image. And in order to detect situation in which a child is left alone, which is a goal of this project, and we can adjust the code to output a label along with the detection result. The result can be used to alert the guardian through the algorithm that can detect when a child is alone. So the YOLO version 5 is a model from the YOLO of computer vision model. So YOLO version 5 is commonly used for the object detection. The reason YOLO was adopted in the project is because its advantages. The YOLO has the fast speed and relatively high accuracy. There are many models with higher accuracy than YOLO, but the most important thing is the project is real time. In the chart of the goal is create the object model y-axis that perform very well compared to the inference time that is x-axis. And preliminary results show that the YOLO version 5 is much more effective in achieving this goal compared to other state-of-the-art techniques. In the chart above, we can see the all variant of YOLO version 5 model is learned faster than efficient than. The YOLO version 5 model is the first object detector that associates the procedure of predicting bounding boxes with class level in the end-to-end differentiable network. The YOLO version 5 network consists of three main parts, that is backbone, neck, and the head. The backbone is a convolutional chain that aggregate the shape and shape image feature at varying granularity. And the egg is a series of layers that makes them combine image feature to make prediction, and head is consume the feature of the neck and perform box and class prediction step. That said, there are a variety of approaches that can be used to combine the different architecture in each major component. The contribution of YOLO version 5 is most important is demonstrating that is integrating breakthrough from other area of computer vision, and that as a collection is improved YOLO version 5 object detection. And this is a graph of the results from the training of the YOLO model. Ideally, the loss is gradually decreasing, and prediction recall and MAP are gradually increasing, and this shows the training of the model went smoothly. And this photo can be viewed after the model has been tested. The model aimed to detect adult, child, and child seat in the photos. And the label on the right or left show the result for the photo extracted into the text files. In the first column, 0 means adult and 1 means child and 2 means child seat. The second to the fourth column or the coordinate value of the left box. The last column is the confidence value for each boxes. And the algorithm I can create, the algorithm I create can determine whether the situation in the photos is safe or dangerous. Safe situation are indicated in green text as the top right of the photos, and the safe situation is one where the child is not alone. Commercially, a dangerous situation is when a child alone in the car. It is displayed in the red text at the top left of the photo accordingly. So therefore, this project demonstrates its performance by detecting children left unattended vehicle using YOLO version 5. A further development of this project would be able to add the vehicle temperature data via temperature sensor to the warning condition. Yeah, that's it.
Okay, thank you for your presentation. Can you hear me?
Yeah, sure.
Yeah, you're really impressive. Okay, my first question is, how does YOLO V5 ensure real-time performance in detecting children in vehicles, and why it's important for the project's success?
The YOLO version 5 ensure real-time performance through its designs, which enable to its process imaging quickly while maintaining high accuracy. This real-time capacity is important for the project success because it allows the immediate detection and altering scenarios where the children are left unattended in the vehicles. And the fast processing speed ensure the guardian can be alerted promptly. Yeah.
Okay, thank you for your answer. And my next question is, so what are the key components of the YOLO V5 in this project, and how do they contribute to its result?
The YOLO version 5 consists, as I said, the YOLO version consists of the three main parts, that is backbone, neck, and head. The backbone is CNN network, the process and shape image feature. Then neck combine these feature and head performance detector box and class prediction. And these architecture allow YOLO version 5 to efficiently detect objects in a variety of conditions, contributing to its effectiveness in this project. Yeah.
Okay, so my last question is, so what are the limitations of the current system, and what improvements can you see for the future iterations?
Current implementation will include the reliance on the specific data set, which may not cover all possible scenarios and basic alert system. And future improvements could include integrating more diverse data set to improve detection accuracy and varied condition, incorporating real-time environmental data like the vehicle's internal temperature, and developing advanced emergency response mechanism. Yeah.
Okay, I think that's it. Thank you.
Okay, thank you.
Can you see my screen?
Yeah.
Hello. Yeah.
Yeah.
Okay. Okay. Hello everyone. So my name is Dong Kim. What I'm going to present today is advancing image processing. So object recognition stands as an important technology integral for systems that require a deep understanding of visual data. We focus on ECE, ECE base, which have revolutionized the way computers see and process image. I believe it will be used in such as healthcare, autopilot, and etc. in the future. So traditionally, the field of a neural network has witnessed two primary approaches. The first involves manually designing models tailored for specific tasks. While this approach allows for customer solutions, it is resource intensive and often lacks the ability to generalize across various tasks. The second approach has been to scale up the size of an existing architecture. However, this method typically leads to increased computational demand and making less feasible. So ECE represents a paradigm shift in neural network design. It overcomes the drawbacks of traditional approaches. So ECE introduced a unique scaling formula where we've set the phi to 1 for simplicity. For this project, we use these factors. We optimize the network steps, width, and resolution. this specific balance enhances the model's performance, striking a balance between complexity and efficiency in image recognition tasks. Okay, at the very beginning, we have input image on the left, which gets processed by the init conv layer. This layer applies a 3x3 convolution operation to the input image, and it's followed by init BL layer, which performs batch normalization. Together, they help transform the input images channels. Next, we enter a loop that creates multiple blocks using the MB conv block class. These blocks are connected in sequential manner, with each block potentially having a different number of channels and striped depending on the depth and with the scaling of the model. As we move through the loop, we encounter more MB blocks, each contributing to the future process. The loop continues until all specified blocks are processed. Finally, we reach the final conv layer, which followed by the BN layer and reload activation, which prepares the model for the last stages. Afterwards, we apply adaptive average plane, which reduce spatial dimensions to create a vector of length 1. This vector is then fed into a fully connected layer to make it class predictions. So we primarily focus on loss and accuracy for the result. On the left side, here's the progression of a simple CNN. Notice the reduction in training loss, but also signs of overfitting as indicated by the increasing test loss in later epochs. EfficientNet, on the other hand, showed a consistent drop in both training and test losses, outperforming simple CNN with a final test accuracy of 75. So EfficientNet has a significantly advanced image recognition, balancing accuracy with efficiency and enhancing visual communication. And key challenges include its high resource requirements, limited data testing, and a need for better model interpretability. Feature direction, it involves developing more research-efficient training, testing on diverse data sets, and improving transparency. And that's it. Thank you for your attention. Any question up here?
Yeah. Hi, I'm your discussant. I will start the question. So my first question is like, MB convolution is really interesting, but like, could you explain more about what is MB convolution and how it works?
Okay, so MB convolution is a kind of building block, especially designed to enhance efficiency. So imagine it like a smart filter that initially expands the input data to capture more features and then process these features in a very research effective way. And finally, condenses the information back to a more compact form. So this process, coupled with an option feature, is called ECE block, allows the network to focus better on the most important parts of the data, and it improves accuracy without any needing extra computing power.
Yeah, okay, thanks. And also my other question is like, EfficientNet is like a trending algorithm, so like, is it popular?
Yeah, I think it's quite popular. So EfficientNet is quite popular in the field of machine learning now. So when I researched it, I found that it has a large number of citations. Besides that, it's well regraded because it strikes a good balance between achieving high accuracy and maintaining computational efficiency. So this makes more flexible for various applications. So from those with a limited resource to more popular systems.
Yeah, okay. And also, would you consider the efficient algorithm to be heavy in terms of computational requirements?
So version 0 and version 1, I think it's kind of pretty light, but so EfficientNet is actually designed to be lightweight. So it offers different versions, so ranging from smaller to larger models. So if you go larger model, yes, it is heavier. And this flexibility allows the user to choose a model that fits their resource constraints without significantly compromising on performance. So you have an option to choose.
Yeah, okay. My last question is, where can we use the efficient net? So which application we can use it?
EfficientNet, from my research, is highly adaptable and can be used in a wide array of image-related tasks. So this includes but it's not limited to image classification. Also object detection. There's a more complex application like autonomous vehicles or medical images analysis from my background story. So yeah, so its efficiency makes suitable for use in mobile or embedded system. That's it.
Yeah, okay. Thank you very much.
Hey there, folks. While I set up, I'll just check the mic is working and say thank you to the other presenters for sticking to the time and making sure I have enough time to present myself. Mike, all good?
Yep.
Yeah, we can hear you.
Great, fantastic. So I'm here to talk about watermarking of large language models. And as a quick aside, watermarking is the embedding of hidden information into text or images that indicates origin. So we're looking at things like you may have seen Shutterstock or Getty Images posted on public domain pictures. In this case, we're trying to embed sort of those secret markings into text. And the reason why we're trying to do this, you've seen all over the news and in your syllabi for classes that LLMs are becoming problematic. Machine content generation is much, much easier than it used to be. And everyone can do it nowadays. So we see these news headlines of how cheating is becoming easier in school when I can just look up the answers on ChatGPT, or we have these fake blogs and websites that are cropping up, fake YouTube channels I've seen a ton of. And then we're even getting, malicious Twitter accounts that are trying to inflame people's opinions of things and set off debates, as well as sway political opinion. So there's a lot of issues and reasons why we might want to be able to detect when this is machine generated. How we do that using the paper that I looked at is through a watermarking engine. So what that does is it takes any generic large language model and it attacks this softmax output. And by manipulating this distribution, it'll inflate some words and deflate the probabilities of others. It can still use all of the words, but we'll get a larger likelihood for certain tokens to appear. Tokens being the fancy name for words here. More specifically, we get this partitioning effect here, where we take about, let's say, 25% of the text that can be output by the language model, and we try and inflate that up to, say, 35%. And over the course of 200, 300, 400 produced words, that becomes a statistically significant deviation here that we see in this modified text. And we use hashing techniques and we store that list for detection later. And what we do for detection is a nice simple z-test. So we say, given this green list of words that we want to do inflate and the base probability of them appearing, what is the likelihood that 25% chance turned into 35%? AKA what is the likelihood that a normal human wrote this? And for most tests, we use a threshold of Z4. Then to mimic the paper, I ran some attacks on that. So one being copy paste or no attack, if I was to generate text and just throw it into a submission. Another being a dilution attack, where I create a paragraph out of my essay, let's say, that's machine generated, and I have to be able to detect just that paragraph. Then we have a replacement attack where certain individual words get replaced here. And I make it harder and sort of pockmark the text. And then even we feed it to another transformer or a paraphrasing model, and ask that to rephrase the whole thing. So the surprising results, obviously, just giving it the watermark text, we're going to see a high threshold, a z-score of 9 here on this prompt. And that obviously succeeds over the threshold, and therefore the watermark is undeterred. Even in dilution and replacement with 200 tokens here, we see 7.2 and 7.0. So replacing a number of the tokens or dropping into a larger set of text was unable to mask that watermark. And what surprised me even was that when I asked GPT 3.5 to totally rephrase a 200-word set of text, it came out with a score of 4.41. And to sanity check this, I asked it to generate a new prompt to the same question asked of the marked model, which was a Facebook transformer. And that passed with flying colors. It was a z-score of -0.5. And there was a follow-up study by the folks that created this watermark that even humans, when given the text, couldn't remove that watermark. Lastly, I added to this this work, there was a GitHub repo associated with it. I created this sliding window detector, is what I called it, that I was worried about these dilution style attacks, where if I put 100 words inside a 1,200 word thesis, let's say, that is going to be able to, at some large magnitude, be able to remove the watermark detection. It may be a z-score of 2 or 3 if only a little segment has this inflated probability of green list tokens. And so what I said is, we're going to break up the text into a number of sections, you can see here, these subsets, and we're going to test each one, and they're all going to be these little sets, and I made them overlapping, so we test each bit more than once, and we make this window bigger and bigger as we continue these passes over the set of text. And what we'll do is we'll identify these hotspots. So they will show up as this portion of the text is machine generated and the rest isn't. And so what I got was results where I would see that the second half of the text was watermarked, or in a case where I pasted into I concatenated the prompt and the response from the marked transformer, I got that only the second half was watermarked, and it was adequately able to, and accurately so, identify what portion of the text was generated and which wasn't. And that allowed the transformer and the watermarking engine to be a lot more robust to these dilution style attacks. So that's all I've got. We saw some real success with this approach, and even GPT 3.5 couldn't defeat it. And I'm all ready for questions if anyone has any.
Yes, I heard the presentation very well. The first question is how does token predict in the language model relate to the need for watermarking in the text generated by these models?
Yeah, so what I think you were saying there is that, so token prediction in models as this softmax output, that's what enables this watermarking engine to work. Because if we just got a single token from the watermark, if we weren't, or from the model, if we weren't able to modify this distribution, then we wouldn't be able to encode these probabilities and change this distribution in a way that is statistically significant and recognizable by a detector. Does that answer that question?
Yep. Thank you. And the next question is, how effective is it in distinguishing between human-generated and machine-generated text?
Yeah, so as we saw here, we've got some fairly high z-scores, 9, 7, 7, and 4, which does pass the threshold. If we recall that from stats that a 3 sigma is 99.7% likely, that's our confidence interval there. Z equals 4 is even higher. There's a real emphasis from this detector on making sure it doesn't falsely flag human generated text as machine generated. There's a lot of, catastrophic implications there where my professor comes up to me and says, hey, you cheated. I put it through this detector and it said you did. If we were to get that on human generated text, it would be a really big problem. But we can see that we've got some really, really high z-scores, making for confidence levels that are very, very unlikely to be human generated. We also saw in changing some of the hyperparameters that you can get these z-scores up to 21, 25 with a much stronger watermark. You can even raise it up to about 15 without degrading the what we call utility of the text, or the quality and the accuracy of it from the model.
Okay, and the next question is, how does it address the challenge posed by deletion style attack in large set of text like essay, new articles, or tweets?
Yeah, so unfortunately, this doesn't address these problems on its own, but it does take a large step in being able to combat them. So, one of the big problems here is that when I go to ChatGPT's website, the text that I get machine generated from there isn't watermarked yet. And it would have to be ChatGPT, OpenAI, that would install this on the back end behind some sort of API with a detector as well. And so it becomes almost like a security problem rather than a machine learning problem at that point, where you have people trying to break this watermark alongside the OpenAI folks trying to protect their hash that's creating these token lists and encoding this text. So they need to be able to install that on all of the popular AI models that are open access for everyone to be able to detect it. And then you'd also need to have people that are running through all this text. Let's say Twitter, now Meta, or now X. It would have to install something on its end that says, hey, if this tweet that you just submitted gets flagged as machine generated, we're going to take it down. Or websites are no longer going to host AI generated content. YouTube scrubs through the transcripts of its video. Is this AI generated? Yeah. So there's a lot of room to go, but this enables the first step and the hardest step, frankly.
Okay, this is my last question. So what are the various type of the take of watermarks in machine generated content, and how does it take impact the effectiveness of the watermark detection?
Yeah, so I highlighted 4 of those here for attacks on the watermark. I'd like to take a look at replacement, especially, which is I went in and changed some of the text myself. I just edited words that sounded weird. I wanted to make it sound more like me. A really typical use of if I was trying to, let's say, cheat on an essay. I grabbed ChatGPT content and then I replaced a little bit of it. And that wasn't able to really defeat the watermark at all. You've got still a z-score gap of 3. And obviously, every step towards z-score equals to 4 is going to be, is going to be harder to achieve. And even, this GPT attack where I said, hey, ChatGPT, can you please rephrase this text in 200 words to just keep it the same size? Is what I told it. And even ChatGPT had a tendency to use a lot of these same words in the same proportions. And as a result, it was still flagged here, as you see with this 4.41, it was still flagged as generated, which was really, really surprising to me, but shows off the robustness of this watermark.
Okay, thank you.
All right, thank you so much.
All right, good job, guys. I think I'll stop the recording.